Okay, let's unpack this. Imagine you want to automate a task, maybe manipulate some text or, do complex calculations really precisely. Where do you even start? What are the fundamental tools that make all that possible in a language like Python?
Yeah, that's a good question. We're doing a truly foundational dive here, really exploring the building blocks of Python. We're talking about functions, which are essentially like reusable mini programs, you could say, and strings, which is Python's incredibly versatile way of handling text. Getting your head around these isn't just syntax; it's about unlocking how you really empower yourself as a programmer.
Right. So our mission today is to distill the most important nuggets from our source material on Python programming, specifically Unit 2. You'll walk away not just knowing what functions and strings are, but why they're so indispensable and how they fit into the bigger picture of writing efficient, clean code. So let's kick things off with functions. They really are like your Python tool belt, aren't they? At a high level, Python gives us two main kinds. You've got built-in functions, which are ready to go right out of the box, and then user-defined functions, the ones you create yourself using that def keyword.
Exactly, the def keyword. And we also learned that those built-in functions, they can be sort of broken down further. You have fruitful functions, I like that name. They return a value, like bearing fruit. And then void functions, which perform an action, do something, but don't explicitly give you a value back.
Okay, so how do they actually work? What are the core mechanics?
Well, fundamentally, it's pretty straightforward. You're calling on a named block of code to do a job for you. The basic syntax is just the function name, then parentheses. And inside those, you put any arguments.
Arguments being the inputs.
Precisely, the inputs. And it's worth noting, some functions don't need any arguments at all. Others might take several, and you just separate them with commas. The way to think about it is, a function takes an argument, that's the input you give it, and then it returns a result after it's done its thing.
Okay.
And inside the function, those inputs you passed, those arguments, they get assigned to variables known as parameters.
Yeah.
So you pass an argument, the function receives it as a parameter, does its work, maybe returns something. Makes sense.
Yeah, got it. Argument goes in, parameter receives it inside. And what's great is that many of the common built-in ones, you don't need any special setup.
Exactly, like abs. Super simple.
Right, abs. It just gives you the absolute value, the positive distance from 0. So like abs 45 is just 45, and abs 100.12 is 100.12. You can just type it in the interpreter.
Yep, it just works. Another real workhorse is len.
Oh yeah, len, that tells you the length of something.
Right, it takes any Python sequence as an argument. And since a string is just a sequence of characters, len tells you how many characters are in that string. Super handy for counting.
Definitely. And then there were max and min.
Ah, yes. They do exactly what they sound like. And max finds the largest value you give it. Min finds the smallest. Like little data sorters built right in.
Okay, so those are always available. But you mentioned needing more specialized tools sometimes.
Right. So functions like abs and len, they're always there. But for more, let's say, computational muscle, that's where Python's modular design really comes in. Think of it like having specialized toolboxes. Many powerful functions aren't just lying around. You need to explicitly import them from their specific module first.
Import them, like pulling in extra tools.
Exactly. For instance, if you want the ceiling value of a number, the smallest integer that's greater than or equal to your number, you need the ceil function. But ceil lives inside the math module.
Ah.
So first, you have to tell Python import math. Then and only then can you use it like math.ceil-45.17, which would give you a nat 45.
And if you forget the import,
Python will complain. You'll get an error straight away. It's crucial to remember that import step for these module-based functions.
Right, so the math module sounds like a serious number crunching powerhouse. Beyond ceil, what other tools does it give us?
It's a treasure trove for numerical stuff.
Yeah.
You get xpx for calculating e raised to the power of x. You get floor x, which is kind of the opposite of ceil. It gives you the largest integer not greater than x.
Ceiling up, floor down. Makes sense.
Precisely. It also has functions like log(x) for natural logarithms and log10x for base 10 logs. Both need positive x values, though. Then there's a more niche one, maybe called mod.
Mod. What's that for?
It's quite precise. It actually returns both the fractional and the integer parts of a number together in a two-item tuple. Imagine you're doing financial calculations or scientific modeling where even tiny fractions matter. Mods captures both parts.
Ah, I see. So it doesn't just round or truncate.
Exactly. Both parts get the original sign, too. And then there's pow, x, y.
Power, right. Like x to the power of y.
Yep. So math.pow 102 gives you an undead pow, redundant pow. Math at 4.4 is 16.0. So remember, you must give it two arguments, the base and the exponent. Forget one, and it's an error.
Good tip.
And of course, square x for the square root, again, for positive x. It's basically Python's scientific calculator, just packaged in a module.
That's a great overview. Now, speaking of absolute values,
Yeah.
earlier you mentioned the built-in apps, but we just heard about fabs from the math module. What's the actual difference there? Why two?
And it's a really good question, and it hints at Python's design philosophy sometimes. Both abs and fabs give you the absolute value, yes. But the differences are subtle but key. First, abs is built in, always there. Fabs you have to import from math. Second, abs is more versatile. It works with integers, floats, and even complex numbers. Fabs, on the other hand, is specifically for floating point numbers and integers which it converts to floats. It's often optimized for speed with floats because it doesn't have to worry about other types.
So performance might be a reason to choose fabs if you know you only have floats.
Potentially, yes. If you're doing heavy float calculations and performance is critical, fabs might be slightly faster. But for general use, abs is usually the way to go because it's more flexible and always available. It's about the right tool for the specific job, you know.
That makes perfect sense. And just to round out the built-ins, there's also round, right? That one's separate from math, too.
Correct. Round is another built-in. Its syntax is round, xn. It returns the number x rounded to n digits after the decimal point. If you leave out n, it defaults to 0, rounding to the nearest whole integer.
Okay. And you mentioned importing modules, like import math. Are there other ways?
Yeah, briefly, there are a couple of main ways. The standard is import module, like import math. This means you always use the module name as a prefix, like math.ceil. Keeps things clear.
Right. Avoids confusion.
Exactly. There's another way you sometimes see from module import, like from math import dat.
Right.
The upside is you can just type ceil directly. No math.prefix. More concise code, maybe.
But there's a catch.
Big catch. It pulls everything from that module into your current workspace. This can lead to name conflicts. What if two modules have a function with the same name? Or you have a variable with the same name? Things can get confusing fast. Generally, import module is safer, especially in larger projects.
Okay, good practice advice. So we've covered Python's ready-made tools. Now this is where it gets really powerful, I think. Creating your own tools, user-defined functions.
Absolutely. Python empowers you to build your own functions for specific tasks. You're not limited. You use the def keyword, as we mentioned. The basic structure is def, name, list of parameters, followed by the code block.
Def, give it a name, list the parameters it expects in parentheses, then a colon.
Exactly. And then, crucially, the statements inside the function body, must be indented.
Indented, usually 4 spaces, right? That's the standard.
4 spaces is the strong convention, yes. That indentation tells Python what code belongs to that function.
Got it. So how does the program know when to run my function?
The flow of execution. This is key. Just defining a function doesn't run it. It's like writing down a recipe. Nothing happens until you decide to actually use the recipe to call the function.
Okay.
Your program starts at the first line outside any function, runs top to bottom. Statements inside a function definition are skipped over initially. They only execute when the function name is called elsewhere in your code.
So the definition has to come before the call.
Generally, yes. Python needs to know the recipe exists before you try to use it. You can technically define functions inside other functions, but that's less common. The inner definition only happens when the outer function is called.
Right. And just to quickly revisit parameters and arguments for these custom functions.
Good idea. When you call your function, the values you send in are the arguments. Think of them as the actual ingredient. Inside the function definition, the variables listed in the parentheses that receive those values are the parameters. They're like the labeled bowls waiting for the ingredients.
Arguments in, parameters receive. Got it.
What about getting results back from my function?
That's the return statement. It's incredibly useful. It does 2 main things. First, it specifies the value the function should send back to wherever it was called. Second, it immediately stops the execution of the function and sends control back.
Stops it early, even if there's more code.
Yes. This is often used for error handling. Say you write a function to calculate a square root. You might first check if the input number x is negative. If it is, you could print an error message and then just return. The function stops right there, doesn't try to calculate the square root of a negative, and control goes back to the caller. It's like an escape hatch.
An emergency exit. I like that. You also mentioned something about composition. Composition is simply the idea of calling one function from within another function. It's like building with Lego bricks. Each function is a small, specialized block. You combine these blocks, calling functions within functions, to build larger, more complex programs. It helps break down big problems into manageable pieces, very important for writing maintainable code.
Makes sense. Build bigger things from smaller, reusable parts. And briefly, you touched on Boolean functions.
Right. Just means functions that return a Boolean value, either true or false. These are super convenient for hiding complex tests. Instead of a long if statement with lots of ands and ors, you could put that logic inside a function, say isValidInput, that just returns true or false. Then your main code just says if isValidInput, which is much cleaner and easier to read.
Very neat. Okay, so functions are like the actions, the verbs in Python. What about the stuff we act on? The data. Often that's text. Let's switch gears to strings.
Absolutely. Strings are fundamental for any kind of text manipulation.
Right.
Simply put, a string is just a sequence of characters. And Python knows it's a string because you enclose it in either single quotes or double quotes.
Single or double, doesn't matter.
Doesn't matter, as long as you're consistent for that particular string. Start with a single, end with a single. Start with a double, end with a double.
Okay. And how do we work with parts of strings, get bits out of them?
That's where slicing comes in. Python uses square brackets for indexing and slicing. Indexing starts at 0 for the very first character.
Yeah.
If your first character is index 0, second is 1, and so on.
Zero-based indexing, classic computer science thing.
Exactly. You can also count backwards from the end using negative indices. -1 is the last character, -2 is the second to last, etc. Now for slicing, you use NM. This gives you the part of the string starting at index n. Up to, but not including, the character at index m. The m index is excluded.
Ah, N is inclusive, M is exclusive. Got it.
Right, and you can leave out indices. SM means start from the beginning up to MSN means start at n, go all the way to the end.
Can we see an example?
Sure. If you have S, Peter, Paul, and Mary, S.5 gives you Peter, index 0 up to, not including 5, S7.1 gives you Paul, and S17.21 gives you Mary.
Cool. And other operations, like joining strings.
Yep, the plus sign plus is used for concatenation, joining strings together, and the asterisk is the repetition operator. Go 3 gives you go, go, go.
Nice. What about going through a string, character by character?
That's called traversal, and Python's for loop makes it incredibly easy. Traversal just means processing each character in sequence. If you have fruit, banana, you can just write for char in fruit, print.
And that prints each letter.
Yep, prints B, then A, then N, A, N, A, each in a new line, very straightforward. Or that neat example, prefixes, JKLMNOPQ, suffix ACK. If you loop for a letter in prefixes, print letter plus suffix.
You jack, cack, lack.
Exactly, jack, cack, lack, and so on. It elegantly combines traversal and concatenation.
Very cool. Now, there was a really important point about strings. Something about them not changing.
Ah, yes, immutability.
Mm.
This is critical and often trips people up initially. It raises that important question. If you can't actually change a string, how do you modify it?
Right.
The answer is, strings in Python are immutable. Once you create a string object in memory, you cannot alter that specific object. To modify a string, what you actually do is create a brand new string that incorporates the changes you want based on the original.
So you're not changing the old one, you're making a new one that looks different.
Precisely. Take greeting, hello world.
Oh,
If you want to change the H to a J, you can't directly change greeting 0. That would cause an error. Instead, you create a new string. New greetings J plus greeting 1.
Okay, so you take the J and then slice the rest of the original string from the second character onwards.
Exactly. Now, new greeting holds Jello world.
Mm.
But crucially, the original greeting variable still points to the unchanged hello world.
Mm.
The original is unaffected. This prevents accidental changes in complex programs where multiple parts might be referencing the same string.
That makes sense. It's a safety feature almost. But does that mean Python is doing more work behind the scenes if I modify a string lots of times?
That's a very astute point. Yes, if you perform many sequential modifications like building up a huge string piece by piece inside a loop, Python is indeed creating lots of intermediate string objects in memory and then discarding the old ones. For small strings, it's totally fine, negligible. But for really large strings and very frequent operations, this can impact performance.
Because of all the memory allocation and deallocation?
Exactly. In those high-performance scenarios, developers might use other techniques, like building up parts in a list first and then using the dot join method to create the final string just once at the end, or using specialized libraries.
Okay, that's a great practical tip for efficiency. Good to know. Now, what about finding things within strings? Searching.
Python gives you the find method for that. The syntax looks like straf1.find, straf2, beg, end. It looks to see if the substring str2 exists within the main string str1. You can optionally tell it where to start searching, WEG index, and where to stop, end index.
And what does it return?
It returns the starting index of the first occurrence of str2 within str1, or the specified slice. For example, str1, this is string example.wow. str2 equals exam.str1.find, str2 would return 15 because exam starts at index 15.
Okay. And if you start searching later?
If you did str1.find str2 10, it still starts searching from index 10 and finds it at 15, so it returns 15. But if you search way past it, like str1.find str2 40, it won't find it in that remaining part of the string.
So what happens then?
It returns -1. That's the signal that the substring wasn't found.
-1 means not found. Got it. And find is a string method.
Yes. It's a function that's attached or bound to the string object itself. You call it using the dot notation. Variable.method name arguments. Strings have lots of useful methods like this. Oh, and for a simpler check, there's the in operator.
Yeah,
you can just write exam in str1. This simply returns true if exam is anywhere inside str1 and false otherwise. It's a quick Boolean check.
Nice and readable. Okay, that covers a lot on strings. What about recursion? That sounds complex.
It can feel a bit mind-bending at first, but it's a really powerful programming technique. Recursion is basically when a function calls itself one or more times within its own code.
A function calls itself. How does that even work?
Well, such a function is called a recursive function. The idea is it breaks a problem down into smaller, identical versions of the same problem. It keeps calling itself on these smaller versions until it reaches a point where the problem is so simple it can be solved directly without calling itself again.
Okay, so there has to be a stopping point, right? Here's where it gets really interesting. For recursion to actually work, there's a vital component, the termination condition.
Absolutely crucial. Think of it as the function's escape plan. A recursive function must terminate to be useful. If it just keeps calling itself forever.
Infinite loop.
Infinite loop, yeah.
Yeah.
Or, more accurately, you'll likely hit a maximum recursion depth exceeded error as the computer runs out of memory to keep track of all the calls. The magic is that each time the function calls itself, it should be with a downsized version of the problem, moving it closer to what's called the base case.
The base case.
The base case is the scenario where the problem is simple enough to solve directly without any more recursive calls. It's the condition that stops the recursion. If your recursive calls never actually reach that base case, well, that's when you get the infinite recursion problem.
So you need the self-call, and you absolutely need the base case to stop it.
Precisely. A classic, elegant example often used to teach recursion is calculating the factorial of a number. The recursive Python implementation mirrors the mathematical definition very closely and shows how concise recursion can be.
Right, factorial. N times factorial of n1 until you hit 1. That makes sense as a recursive pattern. Okay, wow. We've covered a huge amount of ground. So, just to recap for everyone listening, what does this all mean for you? We've taken a deep dive into Python's two main function types, the built-ins you get for free, and the user-defined ones you craft yourself. We looked at how to call them, how to define your own with def, the power of built-ins like abs and len, and importantly, when you need to import modules like math for extra capabilities.
Yeah, and then we switched to strings, exploring how fundamental they are for text. We dug into slicing with those square brackets, traversing strings character by character using for loops, and we tackled that really critical concept of string immutability, the fact you create new strings instead of changing old ones, and why that matters, especially for performance sometimes. We also touched on searching with find and the in operator.
And finally, we dipped our toes into the powerful, if sometimes tricky, world of recursion, stressing that all-important base case.
If we connect this all back to the bigger picture, really mastering functions and strings, it's like learning the core grammar and vocabulary of Python. It's what lets you write code that's concise, that's reusable, and it helps you effectively handle text, which is, let's face it, one of the most common data types you'll deal with constantly. So this raises an important question, I think. How will understanding these foundational elements actually change the way you approach your next coding challenge? Will it spark more elegant, more efficient solutions?
Yeah, that's the key takeaway. Next time you're staring down a complex problem, maybe think, can I break this into smaller, reusable functions, like those Lego bricks we talked about? Or when you're wrestling with messy text data, how can string slicing, or maybe a clever for loop, or one of those string methods help you pull out exactly what you need? The true depth and power of Python, really, it lies in combining these fundamental building blocks in creative ways, just waiting for you to compose something incredible.